Thank you. I'm very excited to be here and be in New York. So to kind of give you a background on my talk, I want to deep dive into one particular monitoring metric that I think is often misunderstood, and kind of go over our thought process on how we evaluate a metric, and then go over our tips for how we monitor the rest of our infrastructure, and then go from there. So I'm John Kelly. I work at Bleacher Report. I work on our consumer team that's focused on the consumer-facing applications, and I've kind of taken a lead role in our monitoring infrastructure, so that's why I'm giving the talk. So the first thing I want to talk about is availability. And so this is a metric that's often repeated, and there's a lot of different definitions for what it means to be available in a microservice, in just a system. Is it even a useful metric to really measure? And so I kind of did a deep dive into this. And so the conventional availability definition is that it's uptime over system time. How up is your service? And then coming from Ruby, I heard Erlang Elixir, there's this myth of this 9-9 availability. And so when I start measuring availability at Bleacher Report, I want to see how close can we get to this metric, and is this even a metric that we should look at? So I found the 2003 thesis where the 9-9s, I believe, is where it first came about. And so when you read it in the context of the actual paper, the 9-9s of reliability was something that someone presented, but they didn't explain how they got that metric. So when I saw this, I was like, okay, back to the drawing board. Maybe 9-9s isn't what we can achieve, but what can we achieve with our system? And so a big key component of this is that we're on AWS, and I'm going to use AWS for a lot of my examples, but it applies to any kind of infrastructure as a service provider that you use, whether it's Google or Microsoft or whatever. And so we have multiple availability zones. So in Amazon, we have multiple data centers. We're in the US East Virginia region. And so Amazon has geographic regions that have a cluster of data centers in them. And then you can be in multiple regions or multiple data centers. So for availability, we're in 5 different data centers in the Virginia region. And we have a load balancer node in each availability zone. So when you provision something on AWS, you provision a load balancer. You might not know that it actually behind the scenes is provisioning that in each data center, in each availability zone that your application is in. So our infrastructure is kind of a user makes a request to our DNS provider, which happens to also be Amazon, and then Amazon will return back our DNS record for the AWS load balancer, which then resolves to the public IPs for these different load balancer nodes, and then behind that is then our Elixir applications. So Amazon provides an SLA about 99.95%. So that's quite a big difference from the 9-9s of availability. And there are some caveats around that, right? So an SLA doesn't mean that this is the worst case. It just means that Amazon is financially incentivized not to drop below that. And so I'm kind of going to use this as a contrived example and say that this is the worst case. Obviously, it's not. But it's also the worst case. It's also not the best case. It could be your availability could be much better than that. So what they define as available is that when I showed you that picture of the different data centers, more than one of them is down. So if only one is down, they consider the whole region still available, and this metric doesn't apply. So this is more than one availability zone is down. So the question now is, can we do better than this? And so if you want to go really complex, you can say, well, what if we were in multiple regions? What if we had a geographically distributed app, kind of like what Netflix does? This adds a lot of complexity to the system, but can it give us a much better availability? So to look at this, the graph I showed you earlier, this is kind of it collapsed. So each of the regions now is kind of collapsed of the previous picture. And we have a user hits the DNS service, and we are provisioning an active passive failover. So let's say Virginia goes down, it would then fail over to Oregon. And so that's kind of the setup that I want to explore. So I did a little bit of math here. So if we have 2 regions of AWS availability, and we get like, what's the chance that that one region is down? And Amazon states that regions are independent infrastructures, and we can treat them as independent events that might happen. So we can say that the chance that both data centers are both down is that long number with zeros and then the 2.5. And so if we convert that back to percentage, we get 6 nines, almost 7 nines of availability, which sounds pretty awesome. And you can imagine if you went to 3, then you'd have even a higher availability across your infrastructure. But unfortunately, things aren't always that simple. So this assumes that we can transparently switch from Virginia to Oregon or back and forth without incurring any kind of penalty. But I did some exploration of this, right? And failover is not a straightforward system. So you have an active passive failover at the DNS level, and you have a TTL on your DNS record. And the way Amazon proposes it is that they have a health check associated with the 2 regions. And so they will pull it, and the lowest it can pull is every 10 seconds. So you could pull it every 10 seconds. And then you have an interval for how many health checks have to fail in a row before you consider the region failed and to make the switch over. And because there's this 60-second caching penalty where the DNS records, the name servers aren't going to be updated for 60 seconds, you don't want to do that, right? Because you're going to incur a minute penalty. So you only want to do it if you're sure the region has failed. So I arbitrarily picked, let's say, 5 consecutive fails to be when I would want to switch regions. So that comes out to about almost 2 minutes. So now we're talking about 2 minutes of unavailability every time I want to switch regions. So that's much different than the seconds I was talking about in the prior slide. And then let's say one region fails 3 times a year. Again, this is kind of arbitrary. Amazon, with that SLA, if we consider that the worst case, one region would fail on an average year of 4 hours a year, around that. But let's say it's only 3 times a year where you have to make this switch. That would be 5.5 minutes of downtime just for switching the regions over. But unfortunately, there's even more complexity involved with this. So 5.5 minutes is already over what 5 nines of availability is. So, and we have some more problems. So another problem is that caching 60-second TTL for the name servers, some ISPs they just ignore it. So even though we said 60 seconds, it might be a day, 2 days, a couple hours before some of our customers get switched over to the new region or still pointing to the one that's failed. So some long tail of our customers in a highly available system, even with this failover policy between regions, are going to get served to the wrong region. Another big issue is that I'm not going to even touch in this presentation is the whole issue of data replication across geographic regions. So if you're not using one of the more region-aware systems, whether that's like Kafka or RabbitMQ with Federation or Cassandra that have these like built in, there's even more complexity you need to add to your system to manage passing state between geographic regions. And then another issue is that we've incurred this at Bleacher Report quite often, is that autoscaling is also something that's not free. So if you provision yourself at 10 instances, and then you say there's a max of 20 instances, and you start at 10 instances, and you get 10x traffic, Amazon is going to autoscale for you, but it's going to take 5 minutes to bring up those servers. And if you're not configured the health check correctly, it might then start taking down the ones that are overloaded, which causes even more issues. So there's workarounds like with this. There's the whole containerization where you can, if you have many different microservices, you can have infrastructure provisioned ahead of time and then just upload those containers spin them up on the already provisioned infrastructure. And then kind of a funny, so there's all these different like issues that you're going to run into. And like one of the funny ones I found is that Google had such a big issue with shark attacks on their fiber lines that they actually had to like spend some time reinforcing them. So you can really like go crazy with this, like all these different scenarios, right? So does any of this really matter? Do you need like these many nines of availability? Well, it depends, right? So if you're doing something like with a pacemaker or something, you want as much availability as possible, and you want to spend to handle all those use cases. But if you're dealing with something like a mobile app, maybe not. One quote I had found from Google was that, put simply, a user on a 99% reliable smartphone can't tell the difference between 4 nines and 5 nines. So you can imagine with like your mobile phone, maybe you're on a train or something, how often does the cellular network fail, right? And the user gets a bad experience. So if it's failing because your system is down or because their network is down, maybe they're not going to even notice the difference there. So where do we go from here? So another thing I kind of stole from Google is that they proposed this other measure of availability that they use for some of their services. And it's kind of to contrast again with the definition I've been talking up to now has been the traditional uptime over system time. And this metric is more business focused, so it's successful requests over total requests. And so we at Bleacher Report kind of took this, and because we're focused on just API, at the API level, almost all our Elixir services are APIs, we took this to be HTTP availability. And so we have our non-500 requests over our total 500 requests. And you might notice that 400s are errors. So you might think, well, why isn't that included? But 400 errors are expected errors, where the system behaved as it should by giving the user an error, where we think of 500s as the system did something we didn't expect, and the customer probably got a degraded experience from that. So to jump back to the picture I showed at the very beginning, so what we do is we have our Elixir apps, and then we have the load balancers in front of them. And so Amazon exposes those HTTP metrics at the load balancer level. And so we grab them and then put them into our monitoring system at that level. So it captures more errors that might not hit the Elixir layer, but might be at the load balancer layer. And another key point when we talk about availability of our systems is that we heavily utilize CDNs. And so at Bleacher Report, we have the luxury where a lot of our content is publicly available. And so we can process it and then push it to a geographically dispersed bunch of data centers, and then have that handle the majority of the traffic, and have nice failover modes where it can serve old content instead of giving a hard error. So I'm going to jump into some of like our like internal like availability for our apps, and so keep in mind that these are at the origin level, and at the CDN level, it would be much higher. So with this new metric of what availability is, our Elixir services over the last month, which are about 9 services I took, we have about 2 nines of availability. Again, that's not at the CDN level, it's just at origin. So most of our requests for many of our services are going to be much higher than that. And so at Bleacher Report, we've kind of made this migration from Ruby to Elixir, and we're almost complete with it. And so I wanted to like find the metric for the Ruby apps to like, say like, hey guys, we have much higher availability with the Elixir. Isn't that great? And unfortunately, the Ruby apps had higher availability. So then I was like, what's going on here? And to be fair, this doesn't include our monolithic Ruby application. This is our microservices. Our monolith is beyond hope for monitoring at this point. So what's going on? Why is there this disconnect here where the Ruby app has more availability? Well, I found this other quote, which is that 70% of outages are due to changes in a live system. And so at Bleacher Report, we moved all our development focus to Elixir, and we only use Ruby apps for maintenance mode. So many of these Elixir apps will have several deploys a day and many infrastructure changes. But our Ruby apps are kind of just sitting there and only being touched when we have some business requirement where we haven't implemented that functionality yet. So all of a sudden that makes sense, right? So when you change something more often, it's probably going to break more often, and just because the Ruby apps being higher doesn't necessarily mean like it's better at availability. It just means that we're not touching it as much. And And so when I look at monitoring, I think of like the first step. If you can take care of 70% of your coverage by monitoring what you change, that seems like the best place to start. So like my first recommendation is to monitor what you change in your system. And so we have this whole like movement now in operations of infrastructure as code. And in the development area, I think we've already, like most companies have jumped onto the source control system. So I think having source control for your code, but also for your infrastructure, definitely captures a lot of information about change. And we take it a step further where we also log all our deploys and have records for who made that change and when it changed. And so we can track when these changes have happened in infrastructure, which has been really key for several production issues we've had over the last year. For having that paper trail, we can quickly correlate our metrics with when something went out and know, okay, this is most likely caused by a change, and then institute a rollback and then investigate from there. So I've kind of touched that already. So we rollbacks are not a bad thing for us. We consider rollback just a normal part of the release process, and we try to make our code backwards compatible so we can use that, utilize that tool without much issue. And then another thing we do is we don't deploy after 3 p.m. unless there's a major issue. So that gives us some office hour times to kind of monitor what happened with our changes and catch that hopefully before everyone goes home. And so once you know with change what's happened, what's changed in your system, the next step I would say is to monitor what's happening right now. And so over the last year, we've implemented centralized logging. And so we have many Elixir microservices and even some Ruby ones, like I mentioned. So Phoenix does a great job where it has this plug already built in called plug.requestID. And so it will generate a random UUID for request and tag it in the logger. And then if you pass an X request ID header in an HTTP request to another Phoenix service, it will automatically then tag it with the same UUID. So we use that system quite frequently to tag our requests across our system and have like a trace of what's happening in our system at any given time. And then we correlate that all in a centralized logging system. We use the Elasticsearch log-Kibana elk stack, but any logging system really works. It's really key, though, to have a centralized place. Imagine as you scale and you have tens of servers or even hundreds of servers, and you're doing the traditional approach of doing tail-F, and you're guessing which request, which node the request is going to be sent to, and you don't know what the load balancer is going to do. So having a centralized place and then having a UUID tagged with everything so you can trace it through the system is really helpful. And so we've open sourced for the Elk stack our plug logging, so request logging at the Elixir level, and then our ecto logging for logging stuff at the database level. And then we added a couple extra metrics to logging around like duration and request headers that are useful for our use case. So definitely recommend like looking at logging and looking at customizing it to your specific use cases. And so I already touched a lot on aggregate availability. But so now that we know what's happening in the system and what changed, aggregate gives us the functionality to know what is it working? Like, is our system working as it should? And so for each of our microservices, we have a dashboard of these availabilities at the origin, and then we have it as a number, and we also have the flexibility to change it to a chart. So if we want to see at what time availability start to dip, we can quickly switch modes and see a timestamp for when availability start to degrade, and then try to correlate that with our log, what's happening in the system with the logs, or what changed. And then the next step, after you know, is your system working or not, you want to have an alerting system in place to know, so you're not monitoring these dashboards 24/7. You have something to tell you when something's not working correctly. And when we connected these to availability, we made the mistake of being very strict about what the availability of the service was over what time period. And what happened was we got a lot of false positives. And so you can imagine as a developer, if you're being woken up at 3 in the morning for a false positive, you're not very happy. And so what can happen is then when the developer comes in the next day, what do? They turn it off. They turn off that alert, or they ignore it the next time it happens because it's always assumed to be a false alarm. So one suggestion I have is to kind of take false positives into consideration and maybe be a bit more liberal with your initial availability metrics, and then kind of tighten them up as you figure out like what's the range of your services over time. And so we have an on-call process. Every week we have a different pair of engineers who are on call. And so we have these different metrics that will hit our developers at different times depending on the severity. So Sev 1s are 24/7, but stuff like a Sev 3 or a minor issue would only be during business hours. So we also kind of make sure that we keep developer happiness in mind when considering alerting. And so like the goal of the on-call team is to triage the issue and ping the relevant team members who can actually solve the issue, or if they know what's going on, they can jump right in. But anyone in the organization can be pinged if there's some issue, and it gives some ownership to what developers are working on in the system. And so it will look like this. We also correlate all these issues to a Slack channel, so that all of our team who's online can, if they happen to be curious, take a look and see if they can proactively see what the issue is. And so after we have alerting, so we know when something's not working correctly, and we know and we're notified about that. The next kind of metric I think of is throughput. So how much traffic are our systems getting? What are the requests per minute? What are the requests per second? Can we do some capacity planning for big events, or even figure out like when do we have the most traffic and when do we need to provision more servers? Because like I mentioned before, it can be up to 5 minutes if you're under provisioned before a server will come online, and during that time, a lot of your customers are going to be getting 503 requests or something similar. And so we monitor throughput at the CDN level. Fastly happens to be our CDN, and at the origin level. So we do both, because if for some reason we get a lot more cache misses, we can know what capacity to expect at the origin level, and be ready for that surge of traffic. And these charts can be really interesting because you can see the cyclical cycle of most users aren't on at 1 a.m., which isn't too surprising. And you can maybe, if cost is an issue, scale down during those periods to save some money, and then scale up in the morning when you see that traffic always is peaking up. And at Bleacher Report, we also have some, because we're around sports, some big sports events like NFL Draft. We'll use these metrics and look at historical, what it was last year or the year before that, and kind of make capacity plans for when we expect like 10x traffic, and be ready for that surge of traffic. So after throughput, the next big metric I think is latency. I think a whole talk could be dedicated to just latency. There's a lot of issues when you're working in the cloud with how to actually measure the time of something and whether you can trust the clock or not, which is all really interesting stuff. But latency is very important because there's been a lot of studies about something like 100 millisecond difference can have a measurable impact on the revenue of the business and also in customer satisfaction. So you really want to keep an eye on that, and you want to keep an eye on it at the end-to-end level, where what the customer is seeing in response times, but also at the component level, so you can have an idea of what the limiting factors of your system are. And so I'm going to kind of walk through like an actual use case we had. So we got an alert around our article system not working. And so with our latency measurements, one thing I forgot to mention last slide is that it's very important to measure at the percentile level instead of just averages. So in this chart, you'll see the purple is average, then we have 95 and 99. And you see on May 1st, on the average, there was this small spike. But it didn't look too bad at the higher percentiles. But this is kind of like a more overall of what our article process is. It touches a lot of microservices. And so we got this on-call page, and we look at the first chart, like what's the latency overall. It looks a little concerning, but not too bad. But then we dug into the specific components, and you see here, like the median is, there's a small spike again, but we saw that at the 95th percentile, we saw 3x response times. And so because we had this chart, we could see that this chart is actually for our old Ruby monolith. So even though the request, the alert was for the Elixir application, we could actually quickly find out that actually the issue wasn't that application at all. It was the Ruby monolith, and that was where the outage was occurring. And so we could direct our focus directly to that and not spend any more time on the Elixir app, which was working perfectly fine. And then the next step, I think, is kind of business metrics. A lot of organizations, I think, kind of treat these as their own thing and kind of classify them as analytics. But if you have this monitoring infrastructure in place and this idea of digging into the different metrics that you have, it doesn't have to be just at the programming or system level. You can add business metrics to your use cases. So in this case, I have our articles processing over time, but if you're like, imagine an e-commerce shop, you might want to capture sales, and maybe alerting on sales is more important actually than what the CPU is at any time, because that has a measurable impact on the business. And then the next step, I think, is system metrics. So these are kind of the metrics that creep up over time. So when I talk about system, I'm talking about CPU, file descriptors, percent of memory used, CPU, network. So these are like something like a memory leak is something that you might not notice over time, but if you have this dashboard in place, you can see it start to, you kind of get an intuitive understanding of what it should be. And when you see after a deploy that it's starting to creep up, you can see that something's not working with the system and start to do an investigation before it hits that 100% and you have an outage. And then the last one I talk about is at the VM level or the Elixir Erlang level. Erlang has a lot of metrics that it actually exposes in its standard library. And so I want to dig into another use case we had at Bleach Report with so the run queue. So this is the article service again. This is in production. This is a healthy Erlang run queue. It fluctuates between 0.5 and 1 for our system. But in this case, we were in pre-production. We were duplexing our production traffic to from the Ruby app to the Elixir app, and then doing it we would fluctuate between 1x to many multiples of traffic to see how it would perform. And so while we were in this phase, we noticed that the Elixir app was using a ton of CPU. And so HTOP is one of the tools I use. And so even when we would turn off traffic so that service was not processing any more traffic, we would see it using 8 cores of CPU. And we're like, what's going on here? And so we dug into and this is the actual debugging picture. So we then dug into what the Erlang run queue was, which unfortunately I didn't save that picture. But the healthy one you saw before was at 1. It was at 26. And so once we saw that, we could see that a lot of CPU is used, even though no more data is coming in, and we're seeing that there's a queue building up of processing. And so we start to explore different reasons for that happening. And what we found out was that there was a developer error where we were expecting a certain type of data, and we were getting a different format. And so what was happening was our pattern matching functions it was calling a function definition we didn't expect. And so it was recursing on itself. So it was an infinite loop. So then obviously, because Erlang is really good at recursion, unlike something like Ruby, there was no stack overflow. So it was doing what it should do, but we were really clueless about what was going on until we saw that. And so if I break it down, there's really 4 things you want in a monitoring system. You want a logging system to know what's happening. You want an aggregate data system to make those charts and capture all those aggregate metrics across your services to know what the availability is, what the throughput is, all these and the system metrics. And then you want to log what changes in your system, because that quote said about 70% of your outages are due to changes in the system. And then you want an alerting system, but you want to be careful about keeping developer happiness in mind, but be able to know when something's going to happen, maybe before the customer even notices. And so we use these different third parties for that, but it really doesn't matter what you use. So like I said, we're using Elk and we're using StatsD to Datadog, but it doesn't matter what time series database you use in my mind. It's really just that you're capturing this data and that you're creating these metrics around your business use cases and what availability means for your system versus a web application, or if it's an embedded application that might have a completely different definition of what a good latency is or what a good availability of your system is. And so in my mind, the easy part is actually writing the code for all this monitoring and getting this and logging stuff. The hard part is building up all these metrics and kind of doing a deep dive like I did on availability and really reasoning about what this means for our organization and whether it makes sense or not. And so these are my references, and yeah, I really appreciate your time. If anyone has any questions.
In some scenarios, unexpected traffic spikes will be things that, well, I guess it is expected it's because you generated content you expect. So a sale, for instance. You expect a lot of traffic because of that. In some organizations, it's a lot more about, like, Reddit post goes out and you get hammered. It's something you can't expect as much. Do you think your monitoring strategy would be different in those scenarios, or do you think the approach is generally the same?
So the question is about getting really bursty throughput, if I'm summarizing that right? So yeah, I'm actually dealing with a problem right now where we can't do it the way we're doing it because we can expect really bursty traffic. And I think that does change how you approach things. What we're looking at is like doing back pressure to kind of put a buffer between our Elixir applications and this bursty traffic, whether that's like RabbitMQ or Kafka or something like that. And then at the monitoring level, at the like architecture level, one approach I've seen is like the serverless approach, which doesn't have Elixir support yet, but I think that will come pretty soon. That kind of, along with container orchestration, you can kind of provision stuff ahead of time and then spread that out across your apps so you don't have to provision. You're kind of over-provisioned already by having all these infrastructure and then having the different containers running across them, if that makes sense. Any other questions?
Wondering if you guys use any of Veeam's built-in hot deployment capabilities, or if you're like integrating in your release process or something like that.
So the question is about our release process. So currently we're using Docker. We want to move to like the Erlang hot releases, but we haven't made that switch over yet. For our deployments, what we do is we do with AWS, we use Elastic Beanstalk. And they have something called a immutable deploy. So it's kind of like a blue-green. What happens is it will keep the existing servers up and bring up the code in new servers. And then once those servers are all provisioned and pass health checks, it will then switch the traffic over with the DNS change. So that's what we're currently using.
What do you guys plan on moving to the built-in view?
That's
I'm curious about what that migration is looking like. What are the keeping you from adopting it right now?
Yeah, so the question's a bit more about our release process and when we're going to switch to like XRM and distillery and stuff like that. So right now we are kind of like, we do have a front-end team who uses Node.js, and we have some legacy Ruby applications. So we're kind of like a polyglot environment, and we have to keep, I think that's up to the ops team when they want to make that switch over and when it makes sense to do so. There's obviously a lot of benefits to getting there, so I think that is somewhere we're going to get to, but it might be a year away or even more than that. One more if anyone has a question.
Yep. Yeah. So you made a brief reference to how you were, how you discovered the problem in the earlier processes from duplicating production traffic. I was curious how I've been looking at a few ways to do this. I'm curious how you were managing that, because that's probably likely to do things like data science. There's some way to compare realistic traffic on staging pre-production traffic.
Yeah, the question is about how we duplex our production traffic to our pre-production Elixir services. So it's actually, we kind of take a pretty straightforward approach, and it's worked well for us so far. Is in the Ruby on Rails app, when we get the request, we just spin it off. We spin off a thread and then do a I forget the Faraday or something like that HTTP request to that service, and then we'll do that n number of times. And because we have a CDN in front of stuff, what we'll do is we'll maybe pass a fake parameter like 1, 2, 3, 4, so it doesn't hit the CDN, and then just have traffic hit the Elixir service directly. And that's worked really well for us. We've done up to 10x Ruby traffic onto Elixir applications, and it's any kind of performance issue, which there aren't really many because of all the great things Elixir brings to concurrency and stuff like that. But if there is an issue, that's been really useful for catching it before it goes out to the customers. Thank you.